So now this is one of the key concepts for statistics, uh, which we call as coverage. Now, what is coverage about? Let's say uh, we uh, we toss a coin, all right? Um, um, let's say India has gone to Australia, and Australia is providing the coin for the toss, right? But the Indian authorities want to ensure that the coin that they're giving is a fair coin, all right? So how do you know whether the coin is a fair coin or not? So how will you know that the coin is fair or not? So what can you possibly do? So they say, okay, fine, we'll give you the coin, you can test it out, but you can only test it out by tossing it, not by putting it into any equipment or anything like that. All right. So what I can do, so maybe I toss the coin 30 times, all right, and I see how many times I've got a heads and how many times I've got a tails, right? And I can kind of get an idea. But even if I was to toss the coin, let's look at this. What I'm going to do is, yes, Salman. Hmm? You understood what's the question here? How many of you clear what's the question? Because this is the fundamental question in statistics. We talk about the mean, we talk about the variance. What can we do then? Because it's something on her end. Everything seems to be fine. She just needs to disconnect and reconnect. She just needs to disconnect and reconnect possibly. I've also messaged her on WhatsApp. Okay, right. So is the question clear? Okay, so tell me, how are you going to address this question? Hmm? How are you going to address this question? The only possibility is you. What is not clear? My voice or the question? Okay, the question is this. India has gone to Australia. Indian cricket authorities think that the coin that they are using is a biased one, and therefore they know what will be the more likely outcome, heads or tails, all right? But we don't know, all right? So but we want to test that coin. We want to ensure that the coin is unbiased, all right? How can we test it? See, they say, okay, here the coin is, you can test it. Toss the coin multiple times, perfect, and check if the mean of the probability is tending towards zero point 0.5, perfect, right? So now let's look at this. I say R by norm, okay, or rather let me just do a sample, right? I say sample. So no, okay, R by norm, and my n is, let's say, 10, size is 1, okay, probability is 0.5. So what am I getting? I'm getting zeros and ones, right? So let's sum it up. I say sum, all right? So I'm summing it up, and then I'm dividing it by the number of coins that I want to have. Let me call it n. I say n is, say, 10, all right? Now I sum it up, so I replace this with n, okay? So let's see what I get. So I should be getting 0.8, right? So 10 times seems to be giving me a very, I should be getting an answer which is 0.5, right? So 10 times will, if I was to toss the coin 10 times, looks like I'm far away from what it should be. I will say, oh, you're giving me biased coin, right? So they'll say, okay, why don't you toss it more? Fine. So I'll toss it 100 times. Okay. So I'm tossing the coin 100 times. Let's see now. So now I'm getting closer to 0.5, but still, so look at it. Every time it is 100 cost coins, right? So, but look, so I toss the coin and I got 0.51, which means the coin is biased. It is not 0.5. So what do? Do I toss it 1,000 times? So what I'm saying is, okay, coin toss is still easier. We can still kind of manage, right? What if your experiment was such that it consumes a lot of time and energy and money to actually test the hypothesis? how long, what should be the size of n? Is the question clear? And is the question interesting also? For me, this was really amazing. That okay, so what should be your size of n? When can you say? So the size of n determines everything, right? To know whether whatever we are doing is significant enough or is it correct or not. All right. So now what we say is let's uh, try to solve this statistically first. Okay. So there is something called a coverage. Basically, what we do is for example, what I had done is I tossed the coin 100 times and then I repeated this experiment. And what am I getting? So I got 0.38, 0.51, 0.55, 0.55, 0.46. If I was to plot it, all right, what am I interested in? I'm interested in seeing what's the range if I was to take that, okay, this is the range within which I'm getting my answers. And can I predict that range? Can I say something about statistically about that range? All right. So this is what is about coverage, and this is what is basically about being able to test your hypothesis. So let's do it this with an example. Though I have shown it to you in a simplistic manner, what I'm saying is, let's say my uh, here's my code. All right. All right. So I'm saying I have a trial size, which is k, which is say the number of times we toss the coin in one trial. In our case, we're tossing it 100 times, right? So we say I have a trial size, so I'm writing a function. I'm calling a library called calibrate because that will be helping me to solve some functions. All right, and so I'm installing that package. But beyond that, let's come to the mathematics part of it. So I'm saying my trial size is k. So I have a function called coverage plot, and then my p values. What are they? I'm saying I want to see the trial. I want to repeat. So in this case, we did our trial size all for 0.5 probability, right? But in reality, we don't know. No? We don't know what is the true probability of the coin toss, right? We don't know that value. So I'm taking a range. I'm saying that my probability values are ranging all the way from 0.1 to 0.9 with a change gap of 0.05. So I'm interested in a probability of 0.1, 0.15, 0.2, and so on. Okay. And then I'm repeating this experiment 10,000 times. Okay. So here we repeated our experiment maybe 6 or 7 times. All right. So I'm saying the number of times I'm taking the trials is 10,000. Okay. So so let's see what we do. So what I'm doing is I'm taking something called a hit ratio. So what is this hit ratio? We're saying if I was to so I'm doing my experiment 10,000 times, all right? Out of these 10,000 times, how many times has my value come in a particular range, all right? So because if I was to just say 0.5, if you look at this data, not even once have I got 0.5, right? But if I was to say there is a range, I say an upper limit and a lower limit, then at least somewhere I can say something about whether the coin has the hypothesis, if whether my hypothesis about the coin is correct or not. All right. So what I'm going to do is uh, just give me a second. So what am I interested in? I'm saying I'm doing the coin toss, and let's for now simplicity's sake just consider one probability. Okay. So this is how I'm distributing my probability from 0.1 all the way till 0.9. Okay. And what am I taking on my y-axis? I'm saying I'm doing a 1,000 coin tosses. All right. So out of 1,000, uh, I say I will take a range. Let's say I'm taking some range. All right. Uh, that how is that range computed? One is my expected probability. All right. So let's say I'm doing a coin toss for a coin which I expect to be a fair coin, which means it should be the probability should be 0.5, right? So I'm doing this experiment for a 0.5 case. So my expected probability is 0.5, but if I was to take the up to 2 standard deviations, right? So up to 2 standard deviations is somewhere around 1.96, right? 1.96. And how do I get this? When I say 2 standard deviations, that means 5% on both sides, which means 2.5% on one side, which means 0.97. Quantile is the probability is 0.975, right? So I do a quantile of that. The quantile will be 1.96. Okay, into square root of what is the probability that I'm seeing, what probability have I seen, which is what I've shown you already with the calculation, right? So we were getting 0.51, 0.5 and so on. So let me call it p hat. All right, so I'm saying p hat into 1 minus p hat, okay, square root of this divided by n, right? We know this standard formula that we have. So we get this range, we get a lower bound and an upper bound because of this plus and minus. So what we will do is we will see how many times the mean value that we got, that is so we were getting this lower bound and the upper bound, right? So we then take all these values, okay, and we say how many times has have I actually come in this range out of the total number of times. So if I'm talking about 2 sigma, which means what, 95% chances are there that the value will be somewhere between these two, right? So I have 95% chances, which means at least 0.9 proportionately 0.95 times if I was to hit this range, I'm doing good. All right, and I will call it coverage. This concept would be called coverage. So this may be a little unclear, but it's okay. We will spend a little more time on understanding this in case it is not clear to you. Okay, but let us do it with experiment, then become more and more clear. So what I did here in the code is clear to you guys. What I have written here, what we did here is clear. What was I doing? This was the case where I was doing it only for probability of 0.5. Okay, and I was repeating this experiment for 100 cases, right? So now if I look at all of these values, so I have 1, 2, 3, 4, 5, 6, 7, 8, right? I have 8 values. Let us first look at the range. So what is my lower bound? My LL in this particular case would be, so I would take all the p hats, all right? So so first what I do is right, so all of the p hats, so each of these are the values of p hat, or rather observed mean, right? So this is the observed mean of the data. So I'm saying if I was to take each of these p hats, okay, and so let me measure this. So q norm, I say q norm 0.975, all right, into square root of, so first p hat is what, 0.38, all right, so I say 0.38 into 1 minus 0.38, which is 0.62, divided by n, which is 100, all right. So my q norm comes out to be this value, 0.0951, all right. Now what I'm saying is I'm adding and subtracting it from the p hat value, which was 0.38. So I'm saying c minus 1 comma 1, all right, into 0.0951, okay, and then I add 0.38 to this. So I get two values, right? So I get a lower bound and I get an upper bound. All right. So I've got a lower bound and an upper bound. Now, what is my hypothesis? My hypothesis is that the probability should be 0.5. So is 0.5 lying in this range? No, right? So it is not lying in this range. So in this case, so for the first test that was there with a value of 0.38, no, we had many. So the test which was with a value of 0.3 has failed, right? So if this is what we had ended up getting, we would have said no, the coin is biased. But what we do is we are repeating our experiment many times. So what am I saying? Let us also do the same experiment for other values. So I also got a value of 0.46. So what am I saying? Let's say I say 0.46 plus C minus 1 comma 1 into 1.96 into square root of 0.46 into 0.54 divided by 100. All right. So this time my range is 0.36 and 0.55. So this is a 95 percentile range, right? Confidence interval. Assuming that the data is, the experiment is normally distributed, right? So now 0.5 falls into this. So if I had only these two experiments, right? What would be my coverage? Or let's just do one more time. One more experiment we'll do. Let's do it with maybe a value of 0.7557. All right. So I'm showing 0.57. Okay. So square root of 0.57 and this will be 43, right? So I get 0.47 and 0.66. Again, 0.5 lies within these two. So if I had these three as my trials, if I had the number of times I'm repeating the experiment is 3 times, and each experiment is 100 coin toss, and finally I get these ranges, right? So now I can say this one failed the test, this one passed the test, this one passed the test. So my coverage would be 2 by 3, right? My ratio, hit ratio is what? 2 by 3. Is this clear? And this 2 by 3 is what I call as coverage. Now, the point is, since I'm taking 95 percentile, now what is happening? Understand this. Between 0.28 and 0.475, either 0.5 lies or it doesn't lie. So when I had done experiment, let's look at the reality of the case. What will happen? I would do once a limited number of repetitions, right? And I've done it, and I'll take a summation of that whole thing, or rather a mean of that. That mean would then give me the standard error also. Those values also will give me the standard error. Using the mean and the standard error, I have computed this range. Now either 0.5 will lie on this range or not, which means there is a 0% probability or 1% probability, right? So therefore I would not say this is not 95% chance that the 0.5 will lie in this. This will be a straight away 0 or 1, yes or no, right, in this range. Okay, but what I want to ensure is that my coverage is high, which means if my experiment was repeated many times, right, I should at least succeed 95% of the times. If I'm looking at 2%, if I'm looking at 2 standard deviations as my confidence interval. Is this clear? Have you understood the difference between though this is the confidence interval, this is not that 95% of the times the coin will fall into this. Okay, the outcome will be in this range. The coin outcome can be either in this range or not in this range. Therefore, the probability is either 1 or 0. But what can happen is that if we can repeat these experiments many times, we want to ensure that the coverage is high. So the coverage should be close to 0.95. Have you understood what we have done here? And how do we make it better? By increasing the size of n. So is the thing conceptually clear to you? Then we'll look at the code and then we'll run our experiment graphically. Have you understood what we are talking about here? You have to be really clear about it. Any doubts? If you're not typing back, it means I assume that everything is clear to you guys. Little bit. Okay. What we will do is we will move ahead with the code. Okay. Maybe the code will make it clear to you. Okay. So now 2 parts to the 0.95. See, look, when I repeated this experiment 3 times, what did I get? I actually got 0.66, which means my actual chances of see, first time I did the experiment and I got some value, all right, based on my trial size of 100, all right. So I did the experiment and I got some value. The chances of this experiment or I would say the size of n, whatever size I've chosen of n, which is 100, is good enough only 66% of the times. Other times it is not good enough, because if I was to repeat the same experiment, what am I getting? I'm realizing that if I had done this experiment 3 times, I would end up having my hypothesis value lie in that range only 3 times, only 2 times out of 3. So is this point clear? Which means I need to increase the size of my uh, sample. So typically what happens is statisticians will typically focus on the 0.95 or rather 2 standard deviations of the this is a norm, right? So you will bother on about 2 standard deviations as the range, okay? And therefore that will become the range. But is the range actually conveying that? So is this clear? It is more like a range on a range. Have you understood this? So Kameshwar got it? Others also got it? Pratik, Lavita, Raghav, Dipankar, Abhishek, Kameshwar? Okay. All right. So now let's look at the code. We move ahead and we. So if you notice this, what we did right now is all uh, only mathematics, what we did here, right? And still natural, still something which is very natural that is happening. All right. So what I'm doing here is we we are uh, so the code that I have, what I have is I have this trial size as k. So I'll keep on changing this trial size. That is what is of interest to me, right? What do I want to finally find out? What is the best size that can take care of my coverage being high enough? All right. And then I'm using different probability values. We will see how we want to see how the trial size matters. So in this case, the coin toss was with a hypothesis probability of 0.5. What if the coin or the success ratio, right, of assuming an event which is either a success or a failure is only 10%? So in that case, do you need still the same sample size to be able to predict or to be able to infer that the success ratio is 10% only, versus a sample size that will be needed when your hypothesis is that the success ratio is 50%? Is my question clear? We start with a hypothesis saying the success ratio is 50%. All right. And then finally we see that for coverage part, we need some sample size, right? Then we say, now that was one experiment. What about an experiment where the success ratio is only 10%? Can I do the 10% wala experiment also with just the same size? Or will I need a bigger size, or a smaller size will do what? Right? We don't know this. So we will see that part also. Is the question clear? All right. So therefore, I'm changing my probabilities also. So so my p-val is this. Okay. So let me just show you what is p-val. So I've executed. I say p-vals. You see? So I have all these values of probability, 0.1 all the way up till 0.90. Okay. And then my k is some standard size that I've fixed. And then number of trials is 10,000. Now I'm creating another function. What this function is doing is, it says number of trials 10,000. Okay. And sizes, trial size, whatever I'm passing. Okay. So and I'm giving some probability to it. So I'm giving an input which is a probability, right? It can vary from say 0.1 all the way to whatever, right? So I'm giving some probability to this function, and I'm giving a trial size, and then I divide it by the trial size. In our case, in the earlier example, we had said 100 is my trial size. Now I'm varying that, right? So it's the same formula that we had here. So I get, what will I get? I will get p hat. Let me solve this for you guys. Instead of in the function, let me do it this way. There's an internet issue. Are you guys facing an internet issue with the audio or something, and the video maybe? Lavita is saying she's facing an internet issue. What about you guys? Okay, Raghav, it is fine for you. It's fine with Debashri also. Abhishek also, it's fine. Okay. So looks like something not all right. Okay, Dipankar also is fine. So maybe the issues with the internet out there, and that also locally maybe the range that maybe either Lavita is getting or what, or maybe what uh, her laptop is able to pull. Okay, I'll continue anyways. So let's though I've created it as a function, what I'm doing is I'm giving some value of k. All right. So I say k is equal to 10. Okay. So I'm going to execute each of these lines. I say k is equal to 10. Then I say trial size is equal to k. Okay. Then I say p vals. Okay. Then I say number of trials. And then I'm defining a function wherein I say hit ratio is what? So again here also for now I say p is equal to 0.5. Okay. So that I don't need to go into the function. All right. And then I say, so I'm executing this. So let's see what we get. So let's look at pH now. Okay. So pH is 10,000 values. All right. Of probabilities. Okay. So I get 10,000 values. Okay. And each of these actually give me what is the outcome for that particular trial. All right. So basically I'm tossing the coin. So it's effectively that I'm tossing the coin 100 times my size, no, so 10 times I'm tossing the coin 10 times and I'm repeating this 10,000 times. Okay. So for each of these I'm getting a probability. So now what I'm doing is I'm finding the standard error. So my standard error for each of these probabilities would be given by this, right? I say q norm into square root of pH. Now notice that the pH is a vector here, though it will work. So this is the beauty of R. We can work with vectors just like they are, any other numbers. So I find out my standard error. Okay. So let's look at the standard error also. Again, this will be a, so standard error will be a vector, right, of size 10,000. Is this very clear? Look at this code. My standard error will become a vector of 10,000 because pH is a vector of 10,000. Are you guys clear on this? Have you understood why the standard error would be a vector of 10,000? It is corresponding to each of those trials actually. And then what I'm doing is I'm saying I take the upper bound and the lower bound. So I'll get another vector which again has a size which is 10,000. All right. Now what I do is my hypothesis mean was 0.5, right? I'm saying how many times has the probability, that is this 0.5, in how many cases out of these 10,000 cases the probability 0.5 lies within the lower bound and the upper bound. Okay. So I have a range which is lower bound and I have a range which is upper bound, right? So what I can do is I say, if I say LL less than P, all right, and I say, okay, so what do I get? What will I get if I say LL less than P? I'll get a series of trues and false, right? Wherever this condition is satisfied, I'll get a true. Wherever it's not satisfied, I'll get a false, right? Similarly, if I say LL less than P and I put another condition, I say UL greater than P, right? P in this case is 0.5, right? So, okay, before that, what I do is I'll just use this condition and let's see if I can. So I say table of this. So I get the false 573 times and a true 94, and so effectively this condition is satisfied how many times? It's satisfied almost 0.94 times, right? The proportion is 0.94, but that's not the only condition that I'm interested in. I want to ensure. So my other condition is what? I say and UL is greater than P. Now let's see what we get. So suddenly, now I have only 88% chance of my probability value lying in this range that we got from the experiment, which means, and this is what I call as coverage. So my coverage is what? My coverage is the trues, right? So 8871 divided by 10,000. All right, so that's going to be my coverage. So what I can do is, instead of this, I can take a mean of this, right? So trues and false, and I'll get 0.887. So instead of saying the table, I can straight away say mean. So is this clear? So this is what I've done here. So far so good. Is it clear now? So what I'm doing is, so I have this value, so I get a hit ratio for one experiment. Okay, now what I'll do is I change my probability. Okay, so I change my probability and I get hit ratio for each of these probabilities, and next thing I'll do is I'll plot it. Okay, so this function is clear, so I'm knocking off this line so that we can actually run it as a function. Even this will be clear. Okay, what I do next is I say coverage is S apply p-vals and hit ratio. So I get different values to this and I call this function again and again. So p-vals was all the way from 0.1 to 0.9. So 17 values here, right? So I call the hit ratio function 17 times and I get a sequence which is, so let's do this. So I execute the hit ratio code. Okay. So I have compiled this function and I already have p-vals compiled. Okay, my k is, let's say, 10. Okay, so I compile these lines of code and then I compile this line of code, which is, I'm saying for each of these p-vals, I want you to see what's p-vals. All right, so p-vals is the sequence. So I say p-vals and then hit ratio. Okay, and I store it in coverage. Let's look at what is coverage. So I get these values. So I get 0.64 is the coverage for 0.1 probability and so on. So coverage for 0.15 probability is 0.79 and this is what I'm getting. So what I do is, let me just plot it. Okay, so I say plot. So p-vals can go on the x-axis, all right, and coverage can go on the y-axis. All right, where did the plot go? Okay, so this is not conveying much. What we'll do is convert it into a line. Okay, so I say type is equal to line. So look at this. What is this conveying to us? It is conveying that now what was my focus? My focus was that I should, let me say, okay, oops. So 0.95 doesn't even show up in this. All right, so I'll replot it. I would say plot comma y limit, all right, is equal to c all the way from, say, 1 to 0 to 1. All right, so I've just changed the scale. All right, so this is what my graph looks like now. Okay, and in this graph I'm drawing a line. So what is happening? I see that if my sample size was 10, the central probabilities are still getting close to 0.95, but all the other probabilities are far away. So lower probabilities or higher probabilities, there's kind of a symmetry around this. Okay, but this will not really be symmetric always. So there you probably need an even larger sample size. What we'll do is, let's just increase the sample size and see what we get. Okay, so is this clear what coverage did? Let me increase the sample size to 100. Okay, so I'm increasing the sample size and I'm executing this lines of code, my hit, and I rerun the coverage, all right, and then I replot it. Okay. So interestingly, looks like if you see the coverage now, it's very, let's also draw the segments line. You see, but even still, there are only some values which will probably be hitting the 0.95. There are a lot of these probabilities which are lower than 0.95 still. Have you got this? What has happened? How we were able to say that what is a good fit? What is the right size? Let me increase it further. Let me make it 1000. Okay. Let's see how we get it now. Where do we hit? So only this. Okay. And then I rerun coverage. Okay. For lower probabilities, it's still not satisfying the condition. Are you getting this? Or maybe for the higher ones. But for the others, it is fitting the bill. Almost. You got it? So shall I go through the further code? But have you understood what has happened here? Conceptually, you should become more clear about it. What are we talking about and what happened here? So this kind of gave me an idea. What should be my standard size? Especially for a coin toss, right? Say 0.5, where can I get a good value? Maybe even at 50 coin tosses. Let's see what we get. I say 50, all right? And my probability of interest is actually 0.5 only, not others. But I still executed for all of them. Are we? Is the experiment getting repeated or not? No, I didn't plot it only. Sorry. I think last time also I didn't plot. Okay, right? So for 50, look, I need to draw the segment line to get a better idea. All right. So even for 50 is not really good enough because not really touching the point, right? So maybe I'll need to make the size larger to be able to predict it with that much level of confidence. Is it clear now? So what are we doing and how we can say what is the whether the sample size that we have taken is adequate enough or not? Have you understood this concept? How many of you have understood this? So right now what I'll do is I'm going to kind of uh, you know uh, run this bigger function which is cover plot. What am I doing there? I'll show you what I'm doing. Okay. I've used a plot line, right? I'm plotting it and then I'm doing this whole thing again and repeatedly, but in the same graph. Okay. So right now what was happening is we were not able to compare for different values of n. So what I'm doing here is we will be able to compare for different values of n. That means everything else being the same. If I was to change my hmm, where I had written some pieces of code here, right? In this might have caused some problem. Can you just help me quickly with being able to identify? All this was fine. Coverage was fine. Color is equal to blue. Can you just see where this? Oops, here. Okay, so we got our function correct, yeah, without any error. So don't bother about this function for now. Okay, uh, so now I'm calling it, right? So what am I increasing? Now I'm increasing the my n size of n. All right, let me begin with 10. Okay, and I go all the way till 30. Okay, so I'm able to change the sample size, right? Earlier we had to kind of only keep it fixed, so I was not able to compare it. So I'm saying my jump, sorry, so I'm saying my values for n val are 10 and 30. Okay, so I'm taking two values, right? And when I say new plot, which means the first time it'll plot it, the next time it will not plot it. Okay, it will just draw the lines on the same plot. So I'm calling the same function, but now I'm doing multiple cases. All right, so I'm calling this function called coverage plot with different values of n. Within the coverage plot, the hit ratio function will be called again. Okay, all right, so do you see this? What do we get here? I have this one. This is for probability of 0.1. All right, sorry, this is for 10, size of 10, right? And this for the size of 30. Is this clear? As we see that the size increases, the sample size increases, my coverage has gone better. But still at the boundaries, there is a problem. Can you relate to this? Have you understood this concept? If you've got it, then I'll move ahead. I, I have created the experiment in such a manner that we can do it for much larger, like whatever values you want. Say, for example, we can do for 3, all right, rather than just 2. So now you see three ranges here. So I have changed my code somehow. Probably that file, there's an older file that has got opened. What I had done is I was printing the actual number of size of the trials here rather than the values where it is maximizing. So what I've done is I've also found out where it is maximizing the coverage. All right. So what I see is in this case it is at 0.5, here it is at 0.65, and so on. In this case it's probably at 0.3. So you can't just say that it will by jump to. Let me just show you. What is the sequence? We say sequence of say 10 to 50 by 12. What does that do? It gives me 10, 22. It's adding basically that number. So jump is basically how many values do you want to jump? Add to that, right? In our case, we said jump is 20 and we said 10 to 50 and 20. So we'll get 10, 30, 50. Got it? So have you got this, understood this, what is happening and what is it conveying to us? How many of you have understood this concept? Then I can move ahead. Abhishek, I mean, Debashri, you got it somewhat. Okay. Okay, what is the question? Ask me. What is it not clear? I will kind of then otherwise just do it on the board now, right? So I've shown you the code. Okay, Kameshwar understood it. Good. Okay. What about Dipankar, Abhishek, Pratik, Raghav? Abhishek, you understood it? Okay. Dipankar, and those who not say like say Debashri. In the meantime, do you want me to repeat this? Because this is a really important concept, okay, which should be really understood well. I don't mind repeating it. This course, especially statistical inference, even I'm going a little slower because I see that the whole thing is about concepts. Like I think Pratik had pointed out to me that we should focus on the concepts, and that's what anyways I'm doing. since we started off after Navratri, you know. So we are still not in the week 3, we are still in week 2. But I felt that this is like I spent almost 3 hours writing this piece of code yesterday. All right, because this simple thing I felt is it conveys a lot. So let me repeat the whole thing. What am I saying? What am I interested in? Let me use a blackboard and pen. Okay. So say let's come back to our coin toss example, right? So the Australian team gave us the coin. Now what am I interested in finding out is how many times should I toss it? All right, so that I can say, so this is what I want to find out. So how many times should I toss my coin? Okay, and this is not what I want to find out after I've got the coin. This is what I want to find out mathematically. All right, so I want to find this out mathematically, and then I will toss the coin. So what is my mathematics part? I say if I was to simulate, if I was to do a simulation, okay, my simulation uh, is for say number of coin tosses. I call it n. All right, which can be either 10 or 20 or 30 or 40, right? So this is one part. Secondly, my probability that I'm expecting, this is my hypothesis, is 0.5, right? So the other part is this, that I already know this probability. What am I going to do now? I say I do 10 coin tosses. All right. I do a simulation. So I'm not tossing the coins yet. I want to know which of these n values I want to pick up. Is this clear? So what I do a simulation. How do I do a simulation? Let's say I do R binom, right? So I do a R binom. So an R binom will, the inputs will be, one is probability. I say probability is equal to 0.5, and then number of times I'm going to toss the coin is n. Okay, and size is what? 1, because this 1 will give me either a 0 or a 1, right? That's how the R binom function works, and that I can relate to tails and heads, right? So now when I do now R binom for this n, let's say for 10, I would get 10 different values, right? And uh, uh, so what I get is, for example, first time I got a 1, right? Next time I got a 0, next time I got a 0, and I got all this, right? So if I was to take the sum of this, I would get how many times I have succeeded, and then I divide it by 10. So I get a ratio. This is my hit ratio, right? How many times I have actually got a success. Now this should be close to 0.5, isn't it? Then only my hypothesis holds, right? This value should be really close to 0.5. In this case, I can get my answers which are like either 0.4 or 0.5 or zero point 0.6, because I'm using only 10 coin tosses, isn't it? So, but I it is very rare that I would get exactly 0.5, right? The probability of getting 0.5 is what? Uh, no, we can't even say it's 10%. It'll be you know probability of getting uh, uh, 5 heads equally, right? Assuming that the coin is fair, the probability of getting uh, it'll be 10c5, right? Tell me, is that what it'll be? So no. Anyways, so will it be 10c5? The probability of getting 5 heads, okay? 10c5 divided by total combinations, which will be what? How does it? So first time I get a probability of heads is 0.5. Next time getting another. What's the probability of getting, if I was to toss the coin 10 times, what's the probability of getting heads 5 times? Sorry, I've lost it. I need help from you guys now. Uh, uh, what will be that value? Uh, what is the formula basically? Tossing the coin 10 times, what is the probability of getting a head 5 times. I'll have probability of getting a heads once, twice, thrice, and so on. Are you guys there? Are any of you working on the maths on that? Wait, let me only put the effort. So if I'm tossing a coin 10 times, which means either I get a heads or a tails, right? A sequence. Now, how many possible combinations are there? Is it 10C2? No. How many possible? Raghav? Who's good with? Something has just skipped out of my mind, the simple formula of probability. So, 10C5 will give me, okay, this into, yeah, I think this will be into 1 upon 2 raised to power 10. Is this correct? This is how it will be? Will this give us the correct answer? Let's just calculate this. So P by norm, or we can straight away use the function anyways. Say Q is 5, size is 10, okay, and probability is 0.5. So, but that is, I think, anything less than equal to 5, right? So this minus probability of P by norm of 4 comma 10 comma 0.5. So it's, I think, is that the correct answer? How do you compute 10C5 in R? Any idea? Is there a straightaway function? There should be, right? What is that function? So anyways, looks like this will be the probability, right? So the chances of getting a, uh, you know, 5 heads is only 0.24, right? So coming back to this, so if we were, so is this clear? We're talking about our hit ratios and everything. So now what I'm saying is, so if I was repeating my experiment, I get a, so this was my, so I'm repeating this experiment with different values of n. Then again I measure my hit ratios, right? And I say, okay, is the hit ratio, so what is the range that I take? So I take a range between which the value should fall to be able to say that I have achieved my success. I can say this thing with 95% confidence that this will be the output. So that is what I do in the rest of the course. The rest of what? Yeah, 0.246, right? So, so let's just revisit this. Hold on. So I'm saying I have a coin which is 0.5 probability of getting heads, right? Which means actually if I uh, toss the coin 10 times, okay, I will get some number of heads, some number of tails. How can I say that the coin is fair? So I have 10 coin tosses. I take this ratio, hit ratio, right? If I was just look at the statistics, uh, I would get the most likely output will be 5 heads and 5 tails, right? But that is possible again only 0.24% times. All right. So only 24% times. The rest of the times you'll get a different answer, but it's still the same coin, an unbiased coin. So now, how can I say that my output is correct? So what I do is I'll draw a range around this 0.5. I say I take the standard error of the mean. So I do a plus minus to this and I add that. So that gives me the range. Now, if my output that I got, whatever output that I got as the hit ratio lies within this range, that means my size of n is all right. If it doesn't lie with the range, then the size of n is not all right. Okay, so let's do this here. I say r by norm. Okay, so size is 10. So there's a number of times I'm repeating the experiment. Okay, sorry, no, we don't want to take r by norm. What we want to do is it q by norm? Which function are we going to? No, we have to generate random numbers only, right? R by norm. Okay, so I'm saying R by norm. N is 10, size is 1. All right, probability is 0.5. Okay, so I get some answers. Let me take a sum of this, rather straight away a mean of this. Okay, so I get 0.4. All right, now to this I add C minus 1 comma 1. All right, uh, let me store it in pH. Okay, so this is my pH, and then I say pH plus C minus 1 comma 1 into square root of P into 1 minus P divided by 10. All right, so I get this range. Okay, now I want to see whether point. So in fact, when I run the experiment, if I was to run the experiment just this much, my 0.5 lies within this, and I could have said, all right, this is fine. But I don't want to just do that. I want to repeat this whole experiment many number of times and then take that ratio. So this is one hit ratio, right? Whether it is lying inside or not. So if it is lying inside, I say 1. If it is not lying inside, I get a 0. So like that, I repeat this experiment many number of times. See, let's say 50 times. So out of 50 times, how many times 0.5 was within this range? Okay, so that is what my coverage is. Is this clear? So if I was to hold on. So let me repeat this. So this case I got a true, right? I repeat it again. This time also I'm getting a true. Wait, why am I getting the same values? Yeah, this time we got a different one, right? So you're getting different ranges. So this case, it didn't fit into the 0.5 bin, right? So we have run the experiment 1, 2, 3, 4, 5 times so far. And out of that, 4 times we have succeeded, 1 time we have failed. 5 times we have succeeded, 1 time we have failed. All right. 6 times we've succeeded, 1 time we have failed. 7 times success, 1 time failure. Okay, 8 times success, 1 time failure. 9 times success, 1 time failure. See, 9 times success, 2 times failure. Are you understanding what has happened here? So I'm getting 9 times success, 1 time 2 times failure, which means my chances, assuming that I was to run this experiment 10 times or 11 times, so I run the experiment 11 times, what am I getting? I get 9 out of 11 times I've succeeded, but that's only 81% times. Not good enough, right? Because I have taken my, sorry, I didn't even take the a factor of 2. All right, I have to consider a factor of 2 also here. Okay, which I didn't. So anyways, so you I think I should have I missed out on the factor of 2 in this? I think so, right? So we are saying that the coin toss thing can be so if I had the factor of 2, then probably everything in all the cases we'd have fit into the range. Maybe a smaller size would have also taken care of us. So is this conceptually now clear to you? What are we talking about? Let me move ahead then. Okay. All right. So this is what was there about coverage. Uh, so now we say this is not good enough, right? So we increase the size. Okay. Another concept is what we normally do is, so many times you can't really increase your sample size. Okay, may not be easy. So you want to compute the coverage. Another way is it's called the Agresti-Colli interval. Whatever answer you got for X, like for example, we got 9 out of 11, right? You add 2 to the successes and 4 to the total sum, all right? And that'll give you a better estimate. So what we'll do is, so 9 out of 11, instead of that, we can say 9 plus 2 divided by 11 plus 4. Basically, we are saying I add 2 success and 2 failures to my output. So I get 0.73 now. So this is giving me a lower result, right? Which means, and typically why this is used is, at least the professor has said that he has found that this gives a better, estimate or a better prediction. So the inference is much better with this rather. This is for small numbers of n, by the way, huh? Not for large n. Okay, and typically you will have n which is small. So this is the how you kind of modify your experiment. Is this fine? So here he has done the same simulation by using that numbers, nothing else. And he says that, okay, this is for coverage where n is equal to 100, all right? And then he's adding 2 successes and failures. And then he gets a coverage which is much higher, but conservative, on the conservative side. Because what are you saying? You're saying I've added 2 successes and 2 failures, which means I've added 50% chance. Earlier, whatever I was computing was at 95% chance, 95% interval. Out of that, then I'm adding some values which are at 50% interval, right? So, uh, so what happens is my result deviates, but this will give me a better picture of what should be my value of n. Okay. So same thing I can do with Poissons. All right. So in the Poissons, we say if suppose a pump has failed 5 times out of these many days, give a 95% confidence interval for the failure. We say Poisson is lambda t, right? So the estimate is x by t and variance is lambda by t. I couldn't figure out why he's saying this. I have to actually compute this, right? So 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 he says, how do you solve this? Okay. I'm not touching this because even I'm not very sure about what he has done here, but he's just done the same thing wherein he's taken that as the standard deviation, all right, and this as the estimation, and then he's computed that using the square root of lambda by t, okay, and q norm is anyways 0.95 and so on. So the Poisson coverage rate is also done doing the same stuff, okay, and you get something like this. Basically what you're saying is that if for small values of lambda, you get a very bad coverage. Okay, as the values of lambda increase, your coverage will become better. Okay, and then he suddenly increased it to 10,000, and the coverage becomes really good. Okay, so you have to summarize this. We're saying that law of large number states that average of IID samples convergence to population means. That is there. So basically, the sample converges to the population means. All right, and CLT states that the averages are approximately normal. Okay, with the distribution which are centered at the population mean, right? So they are normal distributions, and with a standard deviation equal to the standard error of the mean, right? So so basically you get a standard normal distribution. So now what we're saying is that uh, uh, so if we add two if you take the standard error concept, two standard errors works for 95% of the intervals, then we're saying coverage intervals get wider as the coverage increases. What does that mean? What if somebody was to, this is from the lectures itself, say, I don't know if you've seen this movie called Dictator 2 or some Dictator, yeah, right? So this guy asks people to, his scientists to make a nuclear bomb, and he doesn't like the shape of the nuclear bomb, and so because he doesn't like the shape of the nuclear bomb, and he tells the scientist that why don't you change the shape. The scientist said that the shape that you're asking for, if I make that, the nuclear bomb won't work. So and because he refused to do what he was asking for him to do, he just shoots him, right? So he kills the guy. Okay, So now let's say if you were to be very safe, all right, of what you're predicting, you're saying that, okay, I'm giving the election results, but I want to be 95% sure, all right, then what happens? Your range will increase, right? You say that 95% of the chances are the results will be within this. Now, within that lower bound and upper bound, that upper bound and lower bound will be higher as I increase the percentage. If I say only 60% chances, then I can have a narrower lower bound and an upper bound. Is this clear? So the confidence intervals will get wider as the coverage increases. And the reverse, coverage interval will get narrower with less variability as we increase the sample size. That's what we've already seen, right? We just saw this example that as we increase the sample size, the coverage interval will become narrower, right? So either we increase the sample size or we give more confidence interval. Is this fine? So Poisson and binomial cases have exact intervals that do not require CLT. Okay, and I can add 2 success and 2 failures for small sample sizes. Okay, so this one is done. Let me just quickly, I'm not touching it. I just want to, or rather, shall we stop it here? We'll stop it here. Let me discuss certain things that I want to discuss with you all. Is this good enough? Maybe we didn't cover much, but I think this was really interesting and conceptually a good learning. I mean, syllabus wise, we have just finished 50% of the syllabus in this course, means we have finished week 2 today. Okay, so week 3 and week 4 are pending. But I mean, my whole idea is that we should never compromise on learning at the cost of just finishing the syllabus. All right. So all this while, I never felt that this is the first time in the Coursera course that I'm seeing that this course requires more concept building. So even if we are not able to finish the course and we have to take it next month, we will take care of that. But we don't want to rush through the concepts. Is this fine? Are you in agreement with me on this? Or was my pace slow? If you think my pace was slow, then I would kind of make it fast, but I thought this should be kind of explained well, because mathematically if you were to look at it, you would have understood, but unless it goes in thoroughly conceptually, it doesn't make sense. All right, so pace you guys are fine with. You know what, the syllabus I'm still following what is there in the Coursera courses. Only thing is, if I see that whatever they have done is not going to explain the things, I add on to it. Okay, for example, in this course what I'm doing is I'm going to Wikipedia to understand things, all right, or I'm going to different sites wherever I type a question, whatever my clarification is, I sort it out from there, and then I come back to you and explain it that way, right? So syllabus is still what I've read about. By the way, I read yesterday only, I read the reviews. Let me just show you. Okay, so this guy is telling that for this one is he's saying Khan Academy is giving better explanation to this topic. So I'm going to view the whole of Khan Academy stuff hopefully today. At the same time, the swill, it's not an assignment, the swill examples that are given again are very useful. Okay, so we will use the swill assignments mainly to understand the concept. So like for example, our next syllabus is this. If you look at the topics here, uh, week 3. Okay, so week 3 is T confidence intervals, hypothesis testing, and p values. All right, so these 3 concepts we have to learn. Is this fine? Pratik, you got it? Yeah, so that's in fact already there, no? Good enough? Have I are you expecting something more? Okay, so this is what our syllabus is. So we're covering this, and then we move into week 4. I haven't even downloaded the videos, huh? And that's how we will go about it. So uh, so is the pace fine? Let me hear from you guys. Anything that I need to give me some feedback. All right, because uh, Debashri has said it's fine. What about the rest of you? Like for example, today's class, I think we have just covered only 3 or 4 of the slides from Coursera, but I felt that there was a lot to learn from this. That's my personal opinion. What do you think? Pace is good? All right. So Raghav said pace is fine. Salman, what do you think? Kameshwar? Okay, Raghav. See you. Bye. All right. So pace is fine. I think every one of us is kind of agreeing on this. All right. So uh, Saturday, I think the night is not working out because I can't even figure out who's to come, who's not to come. I think we'll stick to morning. Is that okay? All of you guys? Huh? Alternate days, please manage. Okay. Jai Gurudev Salman. What about Sheetal? She didn't come? Bye, Devashri. Devashri, Sarvani is not there today. If you can check what happened.